Hi, welcome back. For this video, I will discuss about the basic modeling in control system, which is we start with the Laplace transform and Laplace inverse transform. So for the modeling specific for electrical system and mechanical system, I will cover later on the next lessons. Right. Before we go to the equations directly from the system to the equation, we go how to know about the complex S-plane, which is here you will know the elements of the transfer function inside the transfer function inside the S domain. Okay, we call this complex S-plane, which is you will plot and you will see the poles and zeros of the equations. Okay, I will tell you after this. Okay, so in this S-plane we have imaginary and we have a real. For the real, we get from here element in the S equations, and for the imaginary value we get here. Let's for example, for this case, we put here the coordinations for the case of the S1, for example. Okay, so let's take a look on example. Let's say we have this form of transfer function in the S domain, which is we have S plus 3 divided by S plus 1 times S plus 2. Okay, so here what you need to know. Okay, you need to extract the equation like this, where is the poles, where is the zeros, and where is the gain constant. The poles will be at the below side of this equation. Okay, this is the poles, and the zero is here at the top of these equations. Okay, so why here is negative and why here is positive. So from here you can get the coordination for the poles. So let's say for the poles we have two coordinations. This one we can make as a S plus 1 equals to 0. Okay, so the S will be negative 1. Same goes to here, is S plus 2 is equal to 0, and S is a negative 2. So this is for the poles. Okay, same goes to the zeros. So you make the same method here. Okay, so for the gain constants, here we don't write any numbers for the gain constants. Yes, because in mathematics point of view, on 1 we don't write 1 here. So if you find that this equation empty without any constant at front like this, so you just make a gain constant as a 1, right? Then you can just draw this real and imaginary axis of plot, and then you can start plot this coordination. For the poles, for example, for the poles they only have a real numbers. Here we don't have a complex numbers, so the coordination for the complex value for this coordination will be zeros. So we only have a real coordination here. Okay, for the zeros we make a circle. Okay, circle for the zeros. Okay, for the poles we make a cross. Okay, you understand? So for the gain we don't have here gain. We don't use gain here. Right, let's say we have non-zero equations. So this equation we don't have a zeros value. We only have a gain here. 2. Okay, and we have a poles, of course. Clearly have a poles. So this is the poles, no zeros. Okay, no zeros, and we have a constant 2. Then we can plot, simply we can plot the same thing, the same process, which is we only have a poles without an imaginary coordination value. Okay, so we plot the poles value on the
real axis here. So let's say we have a more long equation of the S domain here. Okay. So for this case, we cannot simplify this equation, but we can separate this equation by in the form of imaginary value. So here we have imaginary value in coordination either in poles and zeros. Like here we have a imaginary here, imaginary value here for the poles, and of course for the zeros we have here and we have here. Okay, two values imaginary for the poles, same goes to the zeros, and of course the gain is 1 because they don't write gain here. Okay, unless when you simplify you can come up with the some constants other than 1, so then that one become a gain, right? So then we can get the coordinate for the poles, and then we can get for the zeros as well. Simple. For the pole 0, so we goes to the Laplace transform. So Laplace transform is the transformation that we want to get from the time domain to the S domain. Okay, so this S domain we can say that frequency based equation. Before this we in the time based equation. So the theorem of Laplace transform, okay, they have several theorem, okay, several method, okay, but for the subject we simply use the Laplace transform table, which is these tables have shown you the basic components. Okay, after you do some fraction simplification on your S domain equations, so you can use this table to convert all the S domain into the time domain, or a time domain to the S domain. So here let's say we have these simple equations. Find the inverse Laplace transform. So what we're going to do, we search this form, either it exists or not in the table. If not, try to simplify this thing. Okay, and then we go back to the table. Okay, for this case we have this form in the table, so we just convert like this. That's it. Okay, so all right, what is actually the use of this equation? Okay, the ultimate of this learning is we want to get the transfer functions. Let's say we have a transfer function gs. Okay, we can say anything, any symbol for the transfer function. Okay, so let's say gs. Okay, the top area of the functions we call that numerators. So the below ones we call that, the bottom one we call that denominators. Remember this because we always use this one after this. Okay, what is a numerators, what is a dominators part in the transfer function equation. All right. So in this partial fraction form, okay, we have a factor in dominators, which is, this is the theorem, how you're going to simplify when you get the very long or high order uh, transfer function equations. Okay, for example, okay, we have a simple pulse like this. Okay, with the example below. Okay, we have several dominators. Okay, several coordination for the dominators like this, okay, so we need to split this one into by using this theorem. Okay, we need to split this one with a single numerator like this, a1 a2 until an. Okay, for example this one. Okay, how we going to get this one? So you need to the second step, okay, this is the first step. The second step, okay, should be refer this theorem. Okay, you need to split it first, and then the third step you need, and then when you get the split form, okay, and then the step you need to find it in the Laplace transform table, and then you can get this equation as the answer. Right. This is example 3. Okay, let's say we have this fs with the s plus 1 and s plus 2 power of 2. Okay, so we need to split this using this that theorem method first. Okay, second method, and then we goes to the inverse Laplace transform, and then we get the time domain answer. Okay, so for the differential equations representations, okay, we go back to the uh, control system. Okay, here we start entering the control system theory. Okay, which is we need to play around with the transfer functions. Okay, here is a transfer function. Which one is the denominators, and which one is the input? This one is the input, denominators, all right, and denominators as a output or the results. So here how we translate. Let's say we have a system or control systems. We have an input, we have an output, and then we change to the S domain. Okay, and then we put the transfer function like this. We just cover the linear system only. This is a linear system, very simple systems. Okay, all right. So another theorem from the theorem 4 in the differential equations. Okay, uh, we actually let's say we have several differential equation in time domain. Okay, so how we going to express in the S domain? So here it is a Laplace transform method for the differential equations. Okay, whereby we have S near to the Laplace transform equations, additional S. Okay, and then we have an initial condition. Let's say for example we have this differential equation with a second order differential equation for the y. Okay, actually if we consider the initial is 0, okay, and we go back to the Laplace transform theorem equation just now, we can only say that this differential equation, the Laplace transform is like this. This y is represent the S domain for this y. Okay, this is an example. Let's say we have a initial 0. Okay, we have these equations, double differential, single differential, and then we have no differential equation. Okay, as you can see here, double differential, we just take from here. Okay, we just take from this one. So we can get this differential equation uh, in S domain for the double differential, and this for single differential. As you can see here, for single they only have first order S. For double differential we have second order S, and for these um, no differential equations y, so we just put ys here. So this is how we translate to the Laplace transform for the time domain differential equation. Okay, so initial condition for the transfer function is always and must be 0. Alright, so here at the, I can say in the final stage, we would like to create the transfer function for the previous example. Okay, we need to find out which one is the input, which one is the output, which one is the nominators of the transfer function, which one is the denominators. Okay, how we going to extract after we change that equation, differential equation, into Laplace transform? You need to identify which one is the input. For this case, R is the input and Y is the output. Okay, so how we're going to extract is that we take out the ys, because ys is similar for all the components, and then we make it as an output. Okay, and rs as the input. So this is the transfer function equation for this system, or for these equations. This is the transfer function. Okay, I think that's it for this video. So thank you very much for watching. Don't forget to subscribe this channel and also like these videos. If you have any questions or anything to discuss, you can drop down your comment below. Thank you very much. Bye.